I know you're not supposed to have favorite nuclear reactions, but gamma emissions is definitely my favorite nuclear reaction. Let's find out why. We have yet another terrible definition. Gamma emission is the decay of a nucleus by emitting gamma radiation. Great, let's find out what that means. The symbol that we use to denote gamma radiation is the Greek letter gamma, and this font does not show what gamma looks like very much, very well at least. We'll see later on what it's supposed to look like, but we use the Greek letter gamma to denote gamma radiation. Gamma rays are a form of pure energy. So when we emit gamma radiation, we're emitting pure energy. So we're not going to have to change the number of protons or neutrons. There's no change to the nucleus other than we've emitted this energy. They can travel a great distance. There's a lot of energy here. So one thing to keep in mind, though, is that few pure gamma emitters actually exist. And so oftentimes we'll see a gamma emission combined with a positron emission or a beta emission. The damaging power is low, despite having very high energy, because gamma rays are not well absorbed by other materials, but the penetrating power is very high. So when it comes to PPE, if you are working with gamma emitters, you need several centimeters of lead or several feet of concrete between you and the gamma emitter so that you're not coming in contact with these gamma rays. One great example of a gamma emitter used in medicine is cobalt-60. So cobalt-60 is a gamma emitter, and we use cobalt-60 in external radiation treatment. It is especially good to treat tumors that cannot be surgically removed. So this technology has been used since the 1950s in external beam radiotherapy. And so you're seeing the machine, and the patient is lying below the machine. And the machine can focus the gamma radiation into a very narrow beam, directing it just perfectly at the tumor tissue, thereby killing the tumor tissue. So it's kind of an exact way to non-surgically remove a tumor. So we can focus this external radiation on a specific part of the body. This will minimize the damage to healthy cells, but it is not completely, it doesn't just specifically hit tumor cells, it will hurt healthy cells as well. The image that we're seeing is right here. You are seeing a baseline tumor. This was taken October 13th of 2012. And then in a follow-up on January 23rd, 2013, we see that the tumor has gotten larger. So these are our baseline images. So we see that the tumor is growing. After treatment, in the lower left-hand corner, June 20th, 2013, we see a decrease in that tumor. So this is really effective for decreasing these tumor cells. And a final follow-up, August 15th, 2013, we see no evidence of that tumor. So it's a pretty amazing tool in the fight against cancer. Another really neat application of gamma radiation is gamma irradiation, which is used to extend the shelf life of produce. So we take, for instance, strawberries, and we put them on a conveyor belt, and we're going to pass gamma rays through the strawberries. When the gamma rays are passed through the strawberries, any living microorganisms, think bacteria, think fungus, that is being killed on the strawberries. Also keep in mind, gamma radiation is a pure form of energy. So these strawberries are not becoming radioactive. Okay, the gamma ray is passing through them, killing microorganisms. What you get at the end of this process is not radioactive strawberries. It's just regular old everyday strawberries. This has been really great to use in the food industry. So this is not only applied in produce, but we also can pass pork through that too, thereby eradicating any trichinosis that might be in there, any of those pathogen-causing parasites that are terrible. And what you're seeing in this image over here right above me is, on the left, these strawberries have been treated with gamma irradiation, and the strawberries on the right have not, and about 2 weeks has passed. So we can see how much we extend the shelf life of produce. All right, this is definitely one of my favorites because we're emitting pure energy. There's no change in proton number, there's no change in neutron number. Gamma rays have no mass, no charge, so therefore everything pretty much stays the same. So on our cheat sheet, whatever you start with is what you end with. We just include that gamma emission on the product side to show, hey, this is split, this is changed. Oftentimes you will see an M being used, and the M may be with the mass, as we see right here for technetium 99M. And that M designates that this is metastable. So this is a less stable form that has not emitted that, and that kind of helps to distinguish between before and after the gamma emission. Looking at our example, I love these because they're so easy on the brain. We start with technetium 99M. This is the metastable. It will emit a gamma particle. And notice that we take the M off of here. So now it's just technetium 99. The protons don't change. Neutrons don't change. Mass number doesn't change. Okay, the only thing that does change is we go from metastable to the stable form, which is the loss of the gamma ray. And again, no negligible mass, no charge, no nothing to add up. It's a sigh of relief. You knew it couldn't stay that easy forever, right? More commonly, what you're going to see is that your gamma emission is accompanied by an alpha or beta emission. So that's what we're seeing here. We are seeing cobalt-60 going through both a gamma emission and a beta emission. There's my beta particle with a negatively charged electron. Let's take a look at what this looks like. So we have cobalt-60, I'm going to draw my line between reactants and products, with an atomic number of 27. We know in beta emission that we have a neutron that decays to a proton. So my atomic number will increase by 1. Okay, and that's important to keep in mind because that is how we get from 27 to 28, from cobalt-60 to nickel-60. So we now have 28 protons because of that decay. I expect it to be an increase in 1, and those should not be equal. I have 60 minus 27 is 33 neutrons, 60 minus 28 is 32, which makes sense because I've lost a neutron from the reactant side to the product side, and that turned into a proton. The total mass, however, remains the same between my reactant side and my product side. And of course, I'm including my stats for my beta emitter and my gamma emission. Some of our useful medical applications are to take a more stable isotope and bombard it with a particle to make it less stable, because that is a useful thing for us. So we can do the exact opposite of a gamma emission, and we can do a gamma absorption or a bombardment. So we start with a more stable form of our element. We bombard it. Notice that our gamma particle is on the reactant side, and what this does is it creates the metastable version of that element, of that species. So we put the M after that. And be careful, this is a kind of a bad example, but don't confuse that for americium. This is whatever the original mass number was with an M after it. And let's use our technetium 99 example. So we have a more stable form of technetium 99. We bombard it with an alpha particle, creating technetium 99M. Okay, so this is the less stable form. This is ready to emit a gamma particle. Just as in the other examples, our protons are not going to change. This is pure energy. Neutrons aren't going to change. Mass isn't going to change. What is going to change is that we've added gamma energy to form the metastable version of this element. Let's practice. All right, bismuth 214, so I'm going to start by writing that out. Bismuth is atomic number 83, 214 is the mass, Bi is your species. Decays by emission, so we know we're going straight to splitting, and we'll have multiple products of an alpha particle and a gamma ray. So there's my gamma ray, that was the easy one. In alpha particle, we always use helium to show this because mathematically this is just so helpful to show that we have lost 2 protons to the helium and 2 neutrons, and this will help mathematically, and I'll show you what that looks like right now. So doing an accounting, we go from 83 protons to 2 protons plus how many to equal 83? Well, that's 81. Okay, so we have to be able to show that we can add up our protons and have those be equal on both sides when it comes to an alpha emission. The species with an atomic number 81 is thallium, and I'm going to use a lowercase cursive L so it doesn't look like an I and you don't mistake it for, say, titanium, which happens quite frequently. The helium has a mass of 4, so I have to remove 4 from the mass number of bismuth 214, and I get thallium 210. Our final practice problem has us really stretching our brain to find the missing particle, but we can do this. So they want us to give the missing species for the following balanced nuclear equation. Whatever I started with, I wind up with zirconium, which has an atomic number 40, and an alpha particle and a gamma ray. The gamma ray is easy, there's no math to include here, but I do need to account for this change. So I have 40 protons in zirconium, and I have 2 in helium. So this is a total of 42. So my original species had an atomic number 42, which is molybdenum. Tough to read, fun to say, give it a shot. We can do the same thing for our masses. So the mass of zirconium is 90 and the mass of helium is 4. This is a total of 94. So my original species had a mass of 94 and an atomic number of 42.